So today, one way or another, we'll our odyssey through the space of liquid crystals, topics will range from the Higgs boson to the origin of life. So we're not being too ambitious, I hope. Okay, so last time we finished with this calculation of the Friedrich transition. So putting a magnetic field on a liquid crystal molecule, a cell where the molecules are standing up, put a sideways magnetic field on and getting this field-induced tilt. So the differential equation you end up with is this. So the first example I showed was just the simple twist, where we had theta, we have theta equals 0 on the bottom of the cell and pi over 2 on the top of the cell, and just calculating what happens in between to the director. And the solution to that problem was that d second theta dz squared was 0. So that means dm dz of d theta dz is 0. So d theta dz, that's the local increment of rotation. That's the local torque that's being transmitted from slab to slab in the sample. And the derivative of that is 0 means that torque is the same everywhere. So that's the equilibrium condition. So in the middle of the cell, there's a molecule, and the molecule below is trying to turn it to the right, and the molecule above is trying to turn it to the left. And there's no unbalance. And those two things are balanced, so the molecule sits there. Now, in the magnetic field problem, then you get this extra term, which is the magnetic torque. So if there's an external source of torque, then this dz of d theta z is no longer 0, but it's balanced by whatever the external torque is. Now, in a dynamic situation, you can, for example, switch on the magnetic field quickly. Then there's an imbalance of torque. This quantity will no longer be 0 until it gets to equilibrium. So in the sort of transient state, there will be an imbalance of the local torque, and that will produce a rotation. So if this is non-zero, if this quantity is non-zero, then there's a torque being applied locally, and in a liquid crystal, that will produce a rotation. And it's an overdamped, it's like reorienting some object in a viscous liquid. It's an overdamped, viscous response. So you get the terminal velocity times the viscosity equal to the unbalance of torque. This is the basic notion of liquid crystal dynamical behavior. So then you end up with a reorientation time that increases with this viscosity and then decreases with the if you increase the driving force. All right, another feature of pneumatic elasticity is flexoelectricity, and this is kind of a ubiquitous effect in all of these. For example, all the polymer systems where you're producing deformations. Deformations will have associated with them sort of polar ordering, and this comes out very explicitly in pneumatic elasticity. So if you have molecules that have some character of sort of polarity, that is a difference in shape from end to end, and a longitudinal dipole, then if you splay them, you get preferential orientation. And so you get ferroelectric, you get polarization appearing. On the other hand, if the molecules have this character of having a transverse polarization, then when you bend the director, you get transverse polarization. So in nematic phases, you have, you explicitly see these effects. For example, if you make a cell, hybrid cell like this, then you have the polarization associated with the bend in this part of the cell. If you put a field on in this direction, then the plane of this reorientation responds, rotates. So you have in-plane rotation. All right, so now we sort of transition into a new theme, and that's chirality. So we've seen the basic example of this in the cholesteric liquid crystal, where if you make the nematic out of chiral molecules, then you get this helical precession of the orientation. So, kind of a more exotic manifestation of that are the blue phases, where you fill space with the basic structure of packed double twist cylinders. So you have a cylindrical structure with the molecules standing up on the axis, and then as you go out in any direction, they twist. So you get this kind of barber pole structure, which here we just represent by a cylinder. Okay, then you can just pack these cylinders, and in fact, they spontaneously pack into crystal phases. So you can get what's called a blue fog, which is kind of a liquid phase of these cylinders, and then you have various crystal phases. In a temperature gradient, you can actually grow and visualize single crystals of this blue phase. Now, if you look at what happens to the director, you find that this kind of packing requires topological line defects. So this is a simulation of the line defects. It shows that they run along, in this case, they make kind of a double gyroid structure. They typically run along the 1-1-1 directions of these cubic lattices. So this is a lattice of defects where the stability is a trade-off between enabling twist in a chiral molecule at the expense of introducing defects. So typically these happen sort of at higher temperatures in the nematic phase. Okay, so this is a phase diagram of a type 2 superconductor. So vertical axis is magnetic field, horizontal axis is temperature. So at low magnetic field, at low temperature, well, you have a phase transition, and then you get this Meissner phase, which is the superconducting phase in which this conducting system expels magnetic field. Now, in a type 2 superconductor, if you apply a magnetic field, then you induce a phase transition to this vortex phase where the magnetic field penetrates the material in the form of these quantized flux tubes. Okay, so this is a type 2 superconductor. Then you can melt these flux tubes and get a kind of a liquid of them. And then if you go to high enough field or high enough temperature, then you just get a normal metal. So there's a very strong crystal analog to this kind of behavior, which involves what are called the TGB phases. So here in the liquid crystal case, this is just changing the chain length in the tail of this molecule versus temperature. The Smectic A phase is analogous to the Meissner phase. The TGB phases are analogous to the vortex glass. There's a nematic phase, which is analogous to the vortex liquid. The nematic is analogous to the normal metal. All right, so the potential for this kind of analogy was invented by de Gennes. So he argued that in the transition between the nematic and smectic phase, where you have this density wave appearing in the centers of mass in the smectic phase, that's corresponding to the layering. So de Gennes argued that this density wave is formally analogous to the ground state wave function in a superconductor. And he built the theory of this. This sort of summarizes the sort of analogous elements of in these two systems. I don't have time to go through this in detail. What I want to focus on here is the third line. So in the superconductor, the superconducting phase expels magnetic field. In the liquid crystal, the smectic phase expels twist and bend. Okay? So you remember in the expression for the Frank elasticity, there was splay, that's the divergence of N. There's twist and bend. That depends, they're proportional to the curl of N. Now, well, you can see from this drawing that if we try to put a bend of the director on something that's layered, then that drives compression of the layers. Okay.
No, by bend you mean bend of the nematic, not bend.
Bend of the director, right? Not bend of the layers. So we're talking about bend of the director. You can see this quantitatively if you take either a nematic or take one of these systems and you make a trajectory through the phase, calculating this line integral of n dot dl. So if we have a system of layers and we do a trajectory like this on a closed loop, and we get zero contribution here and here, as we go normal to the layers, we're just counting layers. So you go on a closed loop, you count up and then you come back and you count down. So you end up getting zero. So in all these these textures of these photoconic domains I showed, the director in those things has only splay. Twist and bend are expelled. Okay, so, but what if you have a chiral material going from the chiral nematic to the smectic A phase? So now you have a nematic director that wants to be twisted. That's like putting a magnetic field on the superconductor. But this phase approaching that is expelling twist. So now in the chiral nematic part of that story, as you approach this phase transition, the little smectic domains appear in the nematic. They don't like to twist. So in the chiral nematic, you have a certain pitch at high temperature, but as you approach this phase transition, the pitch gets longer and longer because it gets harder and harder to twist. That's how you make mood rings and liquid crystal thermometers. This temperature dependence of this opposition to twist as you approach the smectic phase transition. All right, so there are phases, the twist grain boundary phases, where you actually get both layering and twist. So what happens is that the layering, this happens where the layering is in some sense weak. So you get slabs of smectic layers in which you can have twist, and then you make the twist continuous at the expense of jumping the orientation of the layers. So these blue sheets here are grain boundaries in the orientation of smectic layering that enables twist. So this is a TGB phase. So invented by Tom Lubensky and discovered by John Goodby. We don't have the citation here. So this is an experimental realization of a TGB phase in a smectic phase made of viruses. I'll talk about that in a few minutes. So you can see the precession of the layers. This is like in a wedge cell as you go across. Okay, so now
question, you know.
Yeah, sorry.
So, if this is an analogy to superconductors, so do you have here what's called the pancake vortices, or in the layered material you have these two-dimensional vortices? Is this also something that we can get?
So the question is there an analog of this in 2 dimensions?
Because you see, in superconductors you have layered systems, and
Yeah.
then you have vortices in single layers. You can look at the vortices if it's made out of these what you call pancake vortices, and then the dynamics is a bit different. So I'm just wondering if you have that here also, because you have layered material.
Okay, I don't know that geometry, so it's hard for me to answer.
But here you don't have it, because their pancake vortices are associated with the fact that the crystal material which superconductivity occur is layered.
Yeah.
Here, there's no
There's no-
crystal material, there's just liquid crystal, Smectic liquid crystal. That is a superconductor. It's not an anything else, it's just in the beaker. So there's no, so here these vortices are continuous objects.
All right.
Okay, so then, just in the spirit of, of analogs between liquid crystal, description of liquid crystal systems and possibly related, there's this really interesting idea of David Hughes and Ludwig Liebler, which I guess in light of recent events we should maybe take more seriously. Where, well, we talked about the lyotropic system. So one of the lyotropic phase variations is a sponge phase, where you have a bilayer, one of these lyotropic bilayers, separated in phases with water on both sides. So this is sort of a spontaneous undoing of a lamellar phase into a disordered structure. And I'm not going to discuss this in the detail. They just argue that this lattice gauge model that gives the, that Higgs used to give massed particles through the Higgs boson is identical to a system where you have a lattice with a random interface buying space, and on that basis they calculate this phase diagram for the this kind of sponge phase. In a few minutes we'll have another example, sort of a realization of a sponge phase, although quite a different system. Okay, so we talked about the Smectic phase, where the molecules are tilted relative to the layers. If we make the molecules chiral, then this tilt direction, which is uniform in an achiral Smectic C, responds to the chirality and makes a helix. Okay. So you can shine light perpendicular to this and adjust the pitch of this helix. You can get drag reflection of visible light. So this is kind of one of the basic changes in the Smectic C from a system that's achiral to chiral. Now, a more interesting one was discovered by Bob Meyer. So here we have, so you imagine we have a Smectic C phase, the layers are parallel to the floor, the molecules are tilted, say tilted toward you. Okay. This phase has mirror reflection symmetry in the plane perpendicular to the layers and containing the tilt of the molecules. Okay. But if you make the molecules chiral, then that symmetry is eliminated. Okay, since chirality is handedness. So chiral Smectic C then is not mirror symmetric anymore about the tilt plane, which means it has macroscopic polar ordering in the plane perpendicular to that. So, and the principal manifestation is a macroscopic electric dipole density. Okay, so it becomes locally ferroelectric. And you can put this in a cell with the layers perpendicular to the plates, orient to the polarizers so that so you have this as the possible azimuthal orientations about the normal. So this in the Smectic C, we have this is the local structure, but it's a fluid. So this polarization is free to rotate in this plane. It can have any orientation in the plane. If you put an in-plane field on, then it'll respond to the the azimuthal orientation will change, and you can get electro-optic effects. Okay, so in this scenario, we start with a chiral molecule and a tilted phase. So tilt plus chirality gives polar ordering. Okay, so now there are ways of sort of flipping this story around. And one is the phases of bent core molecules. So this is what we call novo. So it has a banana-shaped core and then these two flexible tails. So because of this bent shape and kind of long molecule, these molecules are pretty strongly layered, and they sort of sterically fit into one another, and so they spontaneously pull in order. So each layer is a ferroelectric fluid. Okay, and then there's a variety where, in addition to polar ordering, so that's a broken symmetry, spontaneously broken symmetry. Then they also tilt as a spontaneously broken symmetry. And so now you have tilt and polarity, they combine to give you handedness. So if this thing tilts, if they tilt to the left, then you have a left-handed layer. If they tilt it to the right, you have a right-handed layer. So then you can make, there are 4 possible bilayer phases depending on how you alternate the orientation of the polarization. Here the polarization's out of the board, here it's into the board, and whether they tilt to the left or to the right. Okay, these are called B2 phases.
These are bananas looking at you, that's the notation.
Here the bananas are this is the structure. So the banana's tilted, so then looking in from here, that looks like this. So that's like that. Okay, so you have, if you just consider bilayers, 4 possible phases. So you can, so there are phases that are homochiral. All the layers have the same handedness, and then there are layers that are unhanded. So this is macroscopically chiral. These are macroscopically racemic. Okay, so these phases so these are spontaneously chiral fluid phases. Now these molecules are achiral. Okay, so the chirality is a spontaneous choice here. So there are lots of examples from the time of Pasteur of achiral molecules that form chiral crystals. So this is the first example of this thing happening this kind of spontaneous appearance of chirality in a fluid. Okay, so then these phases, it turned out, have lots of different manifestations of this spontaneous chiral symmetry breaking. So this is the same material, but now at a lower temperature. So you have a cell between cross polarizers. This is a cell that was heated coming down in the phase sequence, so it goes into these fluid phases and then into what's called the before phase. And then once it gets into the before phase, it looks like this, and you can cool it to room temperature. Actually, the cracks appear as you cool into this lower temperature phase. Okay, anyway, it looks in the microscope, it has this nice blue color between cross-polarizer and analyzer. But if you uncross them, one way or the other, then these domains show up. Okay? So these are conglomerate domains in the language of the chemist. So this is a left-hand domain, this is a right-hand domain. Spontaneously formed from these achiral molecules. Okay, so let me just first say what the structure of this phase is. So this is a phase that's made up of filaments. Okay, and in a neat sample, these filaments are now along these lines here. These filaments packed together in fill space. Okay, the reason the filaments form is that these tilted polar layers have a very strong tendency to be saddle splayed, have saddle splay curvature. They don't like to be flat. Because in a layer, the top half of the molecule is sort of tilted in the east-west direction. The bottom half of the molecule is tilted in the north-south direction. So when you take those two stretched things and try to put them together, then they sort of pop into a saddle splay. And so this local structure, when the phase grows in, forces this growth as a filament. If you try to make the filament bigger, then the layers get flatter, and that suppresses the phase. So this is a self-limiting growth form that is stabilized by this tendency for saddle splay. And these things sort of nucleate and grow, and they transmit their chirality, so you get large areas that have the same twist. So in these regions, all the filaments have, say, left-handed twist, and here they have all right-handed twist.
Can you explain me why they are cell-linking?
Sorry?
Why are they cell-linking? Why? Could you explain me again why
Why are they?
cell-linking?
Oh, why are they self-limiting? So if you if you just take one of these ribbons, so you just have a twisted ribbon. So that has, a twisted ribbon has saddle splay curvature that's maximum in the middle along the axis. But as you go out, the edges of the ribbon, they start out, the ribbon starts out there's an axis up the middle. As you go out to the edges of the ribbon, it twists. As you go way out to the edge of the ribbon, the layers just will gradually become flat. So further out, the layers are flat, but they really want to be saddle splayed, so that costs energy. So rather than make a bigger filament, they'll just grow another one that has the preferred saddle splay. Okay, and this is a liquid crystal. I mean, there's solid-like or hexatic-like ordering in the filaments, but the organization of the filaments is basically liquid crystalline. Okay, so this is the helical nanofilament phase, which is a manifestation of chirality, the spontaneous chirality hearing. You also find at higher temperatures isotropic phases. So this is a phase that has these left and right hand domains. This is with cross polarizer and analyzer. If you uncross the analyzer, then you get domains that are really dark. So they're isotropic, and they're optically isotropic. So these are what are called the dark conglomerate phases. What happens here is that you have layers. You have these fluid Smectic layers, like in the B2 phase, but they can't get flat. Again, because of this local tendency for saddle splay. So the equilibrium structure is a phase of contorted layers. So this is like a sponge phase. You fill space up with these sort of layers. But the layers are continuous, so you can start in a layer and you go along and you can follow the same layer, which is how the chirality propagates. Okay, so this is an isotropic fluid where you have a spontaneously broken symmetry. The only one is handedness.
What are the two colors in that line?
So here, these layers are coming out onto the surface, which is viewed in an electron microscope. So here the layers are kind of coming in perpendicular to the surface, and then here they sort of jump. They jump out of, this layer is going out of the surface, and it gets back in the surface again.
Freeze fracture?
Sorry?
Is this freeze fracture?
This is freeze fracture. Okay. So now we're sort of transitioning into our bio-related topics. And so start with an example of how you can use biological systems to do liquid crystal physics. Not doing the liquid crystal physics of biological systems. We're sort of doing that, but here, this is the group at Brandeis. So they are using FD virus, which is a virus that's about almost a micron long and about 60 angstroms in diameter. So it's a flexible, kind of a semi-flexible polymer. So these have a variety of liquid crystal phases. So this is an image of a Smectic phase. So the viruses are organized, they're oriented, this is in solution, oriented, and they spontaneously will go into Smectic layers. So you get a Smectic phase. They're chiral. So you can also get this twist grain boundary phase that I showed earlier. This is an example of things, of structures you get if you make mixtures of the FD virus with spheres, with spherical colloidal particles, micron scale particles. So then you get phases that are sort of mixtures of spheres in these flexible rods. Very rich, interesting phase diagram. Now, recently they've taken this system, this Smectic, and then added depletant, water-soluble polymer. Okay, so the depletant basically exfoliates this Smectic phase. It comes apart, but the layers stay intact, so the layers separate. gets in between the layers separate. So then you can get monolayers floating around in solution. So this is a monolayer of FD virus, we're looking down on it. So this is like a single membrane, a single monolayer membrane of the virus. You know, you can see it has a surface tension. There are really wonderful movies of this system on YouTube if you're interested. It's chiral. So you see, if you have a Smectic A phase that's chiral, you know, it really, the reactor really wants to twist, as in the, you know, as I mentioned before. But it can't twist in the center of this thing. But as you go out to the edge, then you can get a twist of the reactor at the edge of it, at the edge of this single layer, which they.
It's like field penetration.
Pardon?
It's like London penetration.
Right. Yeah. Okay. So now this is sort of an example of starting to do, you know, seeing, you know, pneumatic liquid crystal ordering and liquid crystal physics in biological systems. So there are, well, you know, an extensive amount of work on the structure of these mitotic spindles, which are basically can be viewed as a pneumatic array of microtubules. But these are active pneumatics, so you have these linear polymerized, you have these linear molecules polymerizing and depolymerizing with transverse connections that are active, molecular motors that are sort of moving along these filaments in a polar way. So this is a recent experiment by Dan Needleman where they use a laser to sort of cut this thing, a femtosecond laser pulse to cut the spindle, and then they can watch the, you know, this sort of this front expand and move across the symbol. It's the spindle. So in this organization, you have a population of filaments that are sort of polymerizing, moving to the right, and then a population that are polymerizing, moving to the left. And, you know, the ones moving to the left preferentially polymerize on the right and depolymerize on the left. So this is a simulation of this. So this is a series of this is a pneumatic of rods. The colors, since these things are polar, this is a polar pneumatic, so the orientation of the polar direction of each rod is given by the color here. And these rods are connected by motors, by walkers. This is actually like a anisotropic elastic gel where these rods are all connected up by elastic tethers. And then if you set them to moving, now you have a form of active pneumatic. And in this particular simulation, what happens is that they phase, they sort of separate. One's going up, separate from the ones going down. That's because if you get the wrong one, if you get a going down one sort of surrounded by going up ones, it ends up going really fast. And so those just more rapidly find their way. They just move faster, and so they always they end up in a place where they slow down. That's where they end up. So. All right, so this kind of introduces a notion of active pneumatics. So here's a system where you just have hard rods. This is a hard rod pneumatic, all on solder, but well into the pneumatic phase. So there are no connections between the rods or anything. Some are up. Again, they're colored according to their orientation. All right, so that's what it looks like in equilibrium. So here, each rod has a force along its axis. There's a constant force applied along the axis of each rod. So each rod wants to move, you know, if there were only one rod, it would just move in a direction at a constant velocity. So there's a force, and then there's basically viscosity. Okay, I can show you. I can go out with this. I don't know if this is, I can find the. Okay. So this is what this thing looks like. So that started from the equilibrium condition, and then as a function of time. You develop these flocks of particles. So,
And the colors again are just the orientation?
just orientation, yeah. Okay. So, equilibrium Luger crystal versus an active Luger crystal. Obviously, lots of interesting things happening here. So,
This is related to, Baha last week talked about, or this week talked about, John Toner and two's clocking problem.
yeah.
Hydrodynamics of it.
Yeah, well, this is
Described by similar
this is kind of the toner situation where you have a high enough density that, the particles
The order, yeah.
are interacting, sterically and strongly. Okay, so then there are a variety of biological situations where liquid crystal phases appear, or you can make liquid crystal phases out of biological components in order to study them. So one example of that is the nucleosome core particle. So Francois Rivolant is looking at the liquid crystal phases of NCPs. So this is the 147 base pair DNA wrapped around a little protein core, so it makes a little sort of hamburger-shaped object, which you can extract as individual units. And these things exhibit pretty rich liquid crystal phase diagram as a function of this is osmotic pressure and concentration. So you get stacking, kind of a la chromonics, but this is in solution again. I'm not 100% sure what the dominant stacking forces are here. Could be electrostatic or just sort of chemical specificity, but you end up with isotropic nematic phases, and then columnar phase, and then these more exotic structures where you get what Cyrus Sapini would call bundling of the columns. course, the canonical liquid crystal biosystem are the lipid bilayers in membranes. And these have been widely studied as liquid crystal systems. I think particularly nice story is that that was developed by Stephen White. So this is a sort of a typical lipid bilayer, in this case lecithin. This motif makes layers, and then you can make a bulk smectic L-alpha phase, bulk smectic A with the crystal by stacking these. Okay, and that's a structure that you can do X-ray diffraction on. Now, I didn't really have time to discuss X-ray scattering physics relative to liquid crystals. It has, of course, very similar to what you learned about X-ray scattering crystals, but there are some kind of fundamental differences. But in this case, well, you know that in protein, say protein crystallization, you can make a periodic array of proteins, and then if you look at the scattering from the intensities of the reflections, you can calculate the structure of the unit cell. And this is sort of the same idea, but in one dimension for this lamellar smectic A. So Steve did a combination of X-ray and neutron scattering, and was able to work out the density, the probability density of all the different groups in this bilayer. So there's a distribution of the choline, that's the head group, the phosphates, the CH2s, and then the CH3s in the tail. So you distinguish, for example, the CH3 from the CH2 by doing selective deuteration in neutron scattering experiments. So by scattering, you can really quantitatively characterize the structure of these lipid bilayers. Now, really, I think, really interesting scenario is this that Cyrus Saphinia has discovered and developed, looking at the structure of complexes of DNA with lipids. Okay, so this was kind of a field that had a lot of sort of notions, but not too much quantitative data, even into the mid-90s. And so Cyrus, in X-ray scattering experiments, discovered that you have phases where you have lamellar reflections in the X-ray diffraction intensity versus wave vector, coming from the lipid bilayers, but then there's an X-ray reflection, and that in the situation where you have DNA mixed in, and that's coming from this intercalated DNA. And you can control the structure of this DNA by varying the ratio of charge to uncharged lipids in the bilayers. You can move this DNA peak around. You can change the curvature of the bilayers by again manipulating the lipids. You can go from lamellar to hexagonal phase, where the DNA chains are sort of surrounded by lipids. He's also so then all these structures are then correlated with the ability of say droplets of these various phases to transfect cells. He's looked at DNA complex with polymer spheres, and then he's gone on to look at the structures of a variety of. This is a lipid bilayer surrounding microtubule with a protein coat. This is in bulk phases, but are sort of isolated objects. Okay, so this brings me to the sort of final story. So, how are we on time?
35 minutes.
35 minutes, okay.
A little more.
Okay, liquid crystals and the origin of life. This will sort of draw on many of the things that I talked about in the last couple of days. Birefringence and chiral nematics and chromonics. I think that, I think the background. We should have plenty of time, so don't hesitate to ask questions. All right, so DNA. Semi-flexible polymer. So this shows DNA adsorbed to a surface, so a monolayer of DNA, and you can see that you get this sort of parallel orientation. So the persistence length is like 50 nanometers, and that's rigid enough for DNA to make liquid crystals. Okay. So you have this is DNA. It's about this is nucleosomal DNA. So I think about 150 base pairs long, 146. Okay, so you make solutions of this, and if you get the concentration high enough, then you get the crystal phases. And so these are chiral nematics. So the DNA is chiral. So the structure actually looks something like this. This is the nematic phase. In the nematic phase, you have a twist of this, of the director. It should take along the long axis of the molecule. Okay. This is actually the structure of the genome in some in these diflagellates. So DNA also has columnar phases at higher concentration. So these phases, the chains pack into a lattice, but they're free to slide along in the direction normal to the lattice plane. So it's a columnar liquid crystal. So it can bend around like as we've drawn here. So you get these sort of curvy, in the polarized light microscope, you get these brushes and these curvy domains, and you can see that you have this this sort of structure. Okay, so I just recall our hard rod phase diagram of the other day. So length and volume fraction. So nucleosomal DNA, if you just look at that rod, it's like 25 to 1 in length over diameter. So that on this phase diagram, that would be sort of here. So as a function of concentration in this nucleosomal DNA, you'd expect isotropic and then nematic and then smectic or in a smectic phase. You actually get a columnar phase because of the polydispersity in length. Makes it preferential for these columns to stack up on one another rather than go into layers. So if you have polydispersity in length, then you lose the entropy gain, the translational entropy gain from getting next to each other, because the molecule or the rods penetrate into adjacent layers and sort of latch things up. Okay, so this is where we expect the nucleosomal DNA to be.
Oh, just a quick question. On the graph that you showed yesterday,
Yeah.
that same phase diagram, it seemed like the nematic isotropic coexistence sort of died off at some point. Does that line keep going forever? Is there a critical point
here?
somewhere? Other
No.
side.
Here, or this
No.
way?
Yeah.
Oh, it just
It just keeps going.
it's sort of, phi goes as 1 over the length, large L. And then at the end, down here, you end up just going directly from isotropic to crystal. It's too symmetric. Okay, so this is the data, and you see this is measurements of the phase coexistence of isotropic and nematic in DNA as a function of length, and you see that there is two-phase. This range in between here is the phase coexistence range, and then there's a phase boundary from nematic to plumber, which also agrees pretty well with this calculation. Okay, so now an interesting question is, so you get pretty much what you expect for 146 base pairs. And if you look at this, then you might wonder, well, how short can you make DNA and still get little crystals? Okay, so I'm going to show you an experiment with these oligomers. Okay, so these are DNA sequences that are self-complementary, which means that they will, when you take one, you flip it over, you will have a duplex, complementary pair of chains, and this will form a short lots-of duplex. And that story is the same for all these. These are all self-complementary. So the short one here has a shape sort of like that, spherical shape, and the longest one has a shape about like that. Okay. So on the space diagram, so those shapes, they're sort of down here. Okay.
So let me ask you something in this, for making this phase diagram, they just consider the exclude volume interaction of this cylinder, of this road?
Well, this phase diagram is simply the excluded volume interaction rate. But you'll see in a minute that this phase diagram doesn't work for DNA. Because all these things, all these oligomers, they all have the crystal phases. Down where this ONSOC, this excluded volume prediction says they would be isotropic. Okay, so the reason for that is that DNA has sticky ends. So the bases are exposed at the end of DNA. So this compares a GC base pair to sunset yellow, which is one of the chromonic liquid crystals. They're about the same. So this end is not very happy in being exposed to water, and so there's an attraction, end-to-end attraction between the oligomers. You can do simulations of that and show that you have in a system of say, this would be like 6 mers with adhesive ends. You have isotropic, nematic, and Coulomber phases. Okay, so what happens here is that You get these complementary oligomers, and so they pair, and you see you get little things like this, which we can just draw like that. Hydrophilic on the side, hydrophobic on the end. These things aggregate. They form end-to-end chain aggregates, linear aggregates, which become anisotropic enough to make little crystal. Both nematic and columnar. Now it turns out that the requirements to get a nematic phase are more stringent in terms of the properties of these aggregates than to get a columnar phase. So if the aggregates are too flexible, if they have a persistence length substantially less than the fully covalently linked DNA, then we wouldn't get nematic ordering. Okay. So the aggregates are fairly rigid, and they get long enough to give nematic phases. And so if you plot a phase diagram of where you have these phases as a function of the length, then you get something that looks like this. In sort of this isotropic domain, you have nematic and columnar phases. So this phase coexistence of these longer guys sort of bending down from the on-solder line, which was not really clear until you look at these really short ones. That's happening, but so there are a lot of liquid crystals then in these shorter oligomers. As you make them shorter and shorter, the transition temperatures go to lower temperatures. So in the 6 base pair, you're kind of at 0 degrees Fahrenheit, so you're below room temperature to get liquid crystals in that thing. Okay, so then you can do experiments with mixtures. So binary mixtures where you have pairs of molecules that are complementary but not self-complementary. This sort of shows what happens in mixtures. So in this, this is a single-stranded oligomers in solution. The yellow ones are molecules that are complementary. So at high temperature, which may be 60 or 70, 80 degrees centigrade, you have an isotropic solution. Okay, as you cool, the oligomers that are complementary find each other in pair. So they form little duplexes. Okay? Then the little duplexes aggregate into chains. And then the chains sort of collect by a first order phase transition into nematic domains, liquid crystal domains, which you can see in the microscope. The birefringent. So, so we have sort of to get to this. There are actually like 4 steps. There's pairing, duplex formation, then there's aggregation, and then there's condensation, sort of assembly of the aggregates. And then there's the organization of. Then you have a phase. So then there's the organization of this phase to get to this point here. Right. So what this is a picture of is So the little bright spots on the right here are a manifestation of complementarity, so they're an expression of complementarity. This sequence of assembly steps will physically separates out the complementary oligomers. Okay, so then that leads to or suggests the following scenario. Suppose we have this situation of, and we add ligation. So, you know, we're going to put chemistry on the ends of these short chains, and that, you know, we'll connect them together. Not enzymatic ligation, non-enzymatic ligation. So, for example, one thing that's being worked on now is to have the little green spots be thiols and the little red spots be enes. Then you can photoligate these chains. Okay, so so now we have this chemistry. So we go back to this situation, and then ask what happens if we ligate. So in this situation, if we ligate, then we are either ligating in the isotropic phase or we're ligating in the nematic phase. If we're ligating in the isotropic phase, then we're just sort of connecting random chains together. If we're ligating in the nematic phase, or in the columnar phase, the crystal phase, then we're connecting chains together, but we're connecting duplexes together. So we're starting with complementary chains and making longer complementary chains. Plus, in this columnar phase, the duplexing and the nematic ordering have, or in the columnar ordering, have put the ligating groups, you know, in very close proximity, so increase their concentration. That promotes ligation. So the liquid crystal ordering selects, it's like a gatekeeper, it selects chains, it selects oligomers that can make duplexes and lets those in. And then it promotes a structure where ligation is accelerated. Okay, so this is our notion for the proposal for how, in, you know, the scenario of life, you go from chemical noise to having some kind of selected set of molecules that you can start the RNA world off with. So this is an idea, sort of, well, to start the RNA world, you need selected molecules. You need something like 30 base pairs, 30 bases in length, or longer. They have to be selected. Of course, there's no life around in the selection here, so the notion is that in this sort of chemical noise situation, liquid crystals can select molecules and create situations where where ligation is promoted. Okay, so let me just finish with this. So then this leads to, well, it sort of leads in many directions, but one experiment that we thought would be interesting would be to make random sequence DNA. Okay, so in this kind of scenario, the sequences don't have meaning until you start getting to this, a situation where molecules have function, and function is sort of demanding particular structures, which then demand particular sequences. So here, sequences have no meaning. So, question is, can you start with a solution of random DNA, random sequences? You made random 20mers to begin with. How will complementarity, will complementarity express itself in if you start off with a solution of random DNA? So this is kind of a random copolymer. Okay, well, what you find is that you make oligomers as a function, you make oligomers of various lengths and look at solutions. So if they're less than about 14 base pairs, there are no liquid crystal phases. But in a range of about 20 to 30 base pairs, you get liquid crystal ordering, and for longer random oligomers, you don't. So the scenario for, okay, so this is the experiment. This is the solution of 20mers. You have these Coulomber phase domains. They have all the characteristics of the complementary liquid crystal structures. They come about in an interesting way. So you have a solution of random oligomers, which means that, each molecule somewhere has a mate, has a complementary oligomer. And occasionally those two will find each other, and so you'll get a fully formed perfect duplex. But that's and that will last forever, because you have 20 bases stuck together. Unless you thermally cycle that, they're basically stuck. That's a very rare event, though. Now, sometimes a molecule will find another one where, say, only 19 base pairs match. Okay, that's a much less rare event. 18 is much less rare than that. Okay. Now, as the number of complementary pairs in an encounter decrease, the probability for that kind of encounter increases, but the lifetime decreases. So if the pairing overlap is less than, say, 7 or 8 base pairs, then they come apart right away. Okay. So there's in 20 random 20 DNA, there's overlaps that involve about 10 complementary bases, have the highest product of probability times lifetime. So the solution becomes basically filled with these things that sort of look like this. They have, half of them are complementary, and then they have these tails sticking out. The tails make these aggregates attractive. So you get end of attraction, which is the basic requirement for getting liquid crystals. So, so you have sort of sections of strong linking, which is the red, and then sections of weak linking, which is the blue. That makes liquid crystal ordering. you make the molecules too long, then they form an isotropic gel, because once you make this sort of 10 or 11 base pair overlap, what's left is strong enough to make another strong overlap. So you get sort of you get gelation in the longer oligomers. But there's a range of about 20 base pairs long where complementarity will express itself even in a solution of random sequence DNA. Okay, so I think that's the end of my story. We had the International Liquid Crystal Conference in Colorado in 2006, and we found this picture to sort of advertise it. I hope you see something like this in your time in Colorado. This is in southern Colorado in San Juan, so it's a big world. I guess, many opportunities to do great things, but difficulties in the process. So, just wish you well in your trek. Next.
This is also the kind of environment where life is very engineered.
Yeah, I mean, it's, seems like the key question is, there's a stage where life makes everything that it needs. But somehow there's a crossover before which it got everything that it needed from the environment, or at least most everything it needed. Just understanding that transition would be really,
But there are arguments in that regard by Albert, Lee Chalbert, saying that what you really need is to be in a non-equilibrium situation at the beginning.
well, I mean,
He talks all about the stuff about vents.
yeah, well, any of these scenarios, you have to have like temperature cycling
Yeah.
and, flow, temperature cycling.
So that's the vents.
Yeah, but just getting enough of the same stuff, obviously, in these experiments, the evolved properties of DNA are relied upon, right? So it would be nice to do this kind of experiment just starting from random mixtures of chromatic liquid crystals, random mixtures of dyes.
Might take 1 billion years.
Well, yeah, so then accelerating that. So, we have a big dye collection we're getting. We're buying lots of dyes. They're really cheap. And so you mix 1,000 dyes and then, see if there's interesting selection behavior and if you can, put in ligation.
But it must have happened at super low concentrations.
But, I think it has to, you have to have concentration. Yeah.
You're evaporating water, just pause, you get fragmentation.
Yeah.
You have the sketch statement that summarizes this, liquid crystals and the original life.
Oh, yeah,
So
so,
that would be good to.
so we go back to here. Right, so the canonical wisdom is that DNA makes liquid crystals because it's an elongated, semi-flexible polymer. Then this scenario says, DNA is a semi-flexible elongated polymer because it makes liquid crystals. So the other statement is at one point, the sole purpose of life was to make liquid crystals.
So now that we've done it, we're done.
So there's a related question a little bit that's he's not here yet, that Sam Safran has been discussing a lot recently. And that's why life, as we know it, our biology works at 100 millimolar salt. And as far as I understand, there are 2 points of view on this. I mean, it's related. One is that, well, we started it with the oceans and they're salty, although they're much higher salt concentration. The other,
They were higher or they're higher now?
the other point of view is that if you have too low salt, electrostatics dominates and you lose all specificity. And if you have too high salt, then everything condenses.
Everything just, you just get it.
So- That's it's sort of fixed there in the say 100 millimolar range.
So does his life,
Well, how do you, I mean, that relates a little bit to the liquid crystalline structure of DNA. I mean, because that truly, because the aspect ratios are salt dependent for sure.
right, yeah. And, you
Do
know,
you have
all
any
the-
comments?
I mean, we've done, if you put it, if you can salt out this whole behavior, I mean, with like high concentrations of sodium, then this stops working. Or if you have like PNAs, for example, with you don't get liquid crystals in PNAs because they're just not interacting strongly enough. So,
These guys might not know what these are.
sorry, PNAs are protein
Protein
nucleic acid. So instead of having this phosphate sugar chain, you have polyamide chain. So they are very, they actually make duplexes that are more strongly base pairing than DNA, but they're not charged, so they don't interact as strong. We don't get liquid crystals from those things. So is life governing well, obviously it's governing our salt concentration. But what's the salt concentration in the ocean?
It's several molar, much higher.
Oh,
What, so you said it disappeared, the liquid crystal behavior disappeared at high salt concentrations. What's high in that sense?
sorry, what?
Like how high can you go?
Oh,
Just order of magnitude.
between, like molar.
So was the ocean in the past much salty than now, or like much less? Much less salty.
That I'm not sure. Okay.
I guess I sort of missed the main point. Why was it important for the origin of life? I guess that was your argument. Why was it important for the origin of life, for the DNA to form liquid crystals? Why was it the selection mechanism?
Well, I mean, the current scenario is, the kind of its main transition to life is the RNA world. So where RNA becomes a catalytic and, autocatalytic and sort of functional, functional family of molecules. But it just seems like there must be, steps before you get to that, which, involve selection and replication. And you need some family of sort of starting materials, where you have you have the same stuff, you have there's so many, to get a functional molecule like a 35 base per RNA, there's so much entropy, the entropy is, sort of totally gone. So, what are the stages that, lead up to that situation? So, this is, we see that in liquid crystal, in this liquid crystal formation, you have this, the series of assembly steps that takes out the entropy, but it leaves you with something that's fluid, so you can still do chemistry. So, it's a scenario for this happening. I mean,
But you're saying that if it didn't form a liquid crystal phase, it would not be fluid and would not, this chemistry would
no,
not.
I mean, the liquid crystal phase, to get the liquid crystal, then, you have to, if you just start from a population of polycyclic aromatic hydrocarbons, so these are things, again, they're just some molecule with some, with something on them that makes them soluble. If they don't have the things on them to make them soluble, then then there'll just be some, some lump somewhere. But some of these will be soluble. Some, so then there are a variety of ways of making them soluble, but, so now you have a population of these. If you concentrate a solution like this, if you get liquid crystal domains, then the molecules have passed a certain test. They're anisotropic enough, they have kind of the right association in terms of the charges to, to orientationally order. Okay, so that's a selection step. I mean, it's a selection step that looks like what's happened in DNA, right? DNA is a stack, is a chromatic stack. So,
So you're saying that if there is some order, it will be easier for it to go, to do the next step and create even more order, that sort of thing?
yeah, because you're doing, the liquid crystal ordering is the selecting, is doing selection. And in the, in the case of these duplexes, it's a multiple step, multiple step selection. So, it's pretty selective.
Quick announcement.